The vibrations that give rise to the absorption of infrared radiation are the vibrations of the atoms in a molecule. As these can be quite complicated, we will start with the most simple case, the vibration of a two-atomic oscillator. We will first discuss the vibrational frequency and later the absorption of energy by the oscillator. The two atoms have masses m1 and m2. The equilibrium distance between the two atoms is denoted by r, and we can think of the molecule as two balls connected by a spring. We denote the force that holds the two atoms together by F and the deviation of the actual distance from the equilibrium distance by delta r. In the harmonic approximation, Hooke's law is valid, which says that the force F is proportional to delta r, the deviation from the equilibrium distance. The proportionality constant is the force constant and denoted by K. Force F is equal to the negative of the force constant times the deviation from the equilibrium position. Just as a note, I want to mention that the SI unit for the force constant is Newton divided by meter. There's also a further unit which uses the unit of force in the CGS system called dyne. The relationship between these units is the following. 1 millidyne per angstrom equals 100 newtons per meter. Solving Newton's equation with this expression for force, we can calculate the vibrational frequency nu of the two-atomic oscillator. Nu equals 1 divided by 2 pi times the square root of force constant K divided by a quantity called reduced mass. The reduced mass is calculated from the two masses connected to the spring according to this equation here, where the reciprocal of the reduced mass is calculated by adding the reciprocals of the two masses m1 and m2. Now I want you to stop the video, look at the equation for the vibrational frequency, and analyze how force constant and mass influence the vibrational frequency. Reflect on what this means for the vibrations of molecules. The frequency increases when the force constants get stronger. This happens when the bond between the atoms gets stronger. Therefore, stronger bonds generate vibrations with higher frequencies. For example, double bonds vibrate faster than single bonds. The smaller the masses, the higher is the frequency. Therefore, bonds with light atoms, like hydrogen, vibrate faster than other bonds. We will now discuss the different types of vibrations that occur in molecules. There are stretching vibrations, bending vibrations, and torsional vibrations. In stretching vibrations, the length of the bond changes. Stretching vibrations are abbreviated by the Greek letter nu. Here. In bending vibrations, the bond of a three-atomic fragment of the molecule oscillates. This is similar to the movement of scissors, and some of these vibrations are called scissoring vibrations. Bending vibrations are abbreviated by the Greek letter delta. In torsional vibrations, the dihedral angle of a four-atomic fragment of the molecule changes. A good illustration for such a movement is the twisting of an eraser. Torsional vibrations are often abbreviated by the Greek letter tau. In the above discourse, I have used bond length, bond angle, and dihedral angle to describe the movement of the atoms. These are structural parameters that relate several atoms within the molecule. Therefore, they are also denoted by the term internal coordinates. A different type of coordinates are, for example, Cartesian coordinates, which are defined with respect to an external coordinate system.